Hello and welcome to the sixth of the Quest tutorial videos. In this video I'll be talking a bit more about Overtone NMR spectroscopy. So for example, it's well known that for spin 1 nuclei, they are highly affected by the first order quadrupolar interaction, which broadens the lines pretty severely. Although any symmetric transition is not affected by the first order quadrupolar interaction, so we can actually observe the first overtone transition for nitrogen-14, for example, and this one will be free of the first order quadrupolar broadening. So if you go to the center frequency and then set overtone frequency and the first overtone, there's only one overtone frequency for spin 1. You can see that the calculated NMR spectrum is actually fairly sharp compared to the full single quantum transitions. And this spectrum actually has a certain line shape. And what's actually very interesting here is that the overtone NMR spectra aren't really NMR because they depend really on the extra terms which don't commute with the Zeeman Hamiltonian. And so this is the overtone NMR spectrum for an asymmetry parameter of 1 for a spin 1 in a coil perpendicular to the magnetic field. So this is the default. Although the one thing that's very special for overtone transitions is that the intensity of the lines actually depends quite strongly on the orientation of your coil. So for this reason I added the option to change the coil angle in this case. Typically the intensities are calculated as the square of the magnitude of the expectation value of the Sx operator. So this corresponds to a coil along the x-axis, and so for a coil at 90 degrees from the magnetic field. It's also possible to change the coil angle just by adding a certain effect from the Sz operator when you calculate the intensities. And so you can change the coil angle, for example, to 0 degrees, so parallel to the magnetic field. And you should actually see some intensity from these transitions, even if your coil is parallel to the magnetic field. So I'm just going to set this back to 90 degrees. And I want to show one thing. So this is the full NMR spectrum where we see the single quantum transitions here. And the little bump here, I don't know if you can see it, is the overtone transition. And if you change the coil angle, for example, to 40 degrees, you'll see that the relative intensity of the overtone goes up a bit relative to the single quantum transitions. And if the coil angle is at 0 degrees, then these single quantum transitions are actually severely reduced, but not completely reduced to 0. And then the overtone transitions are significantly more intense. So often the line shape from the NMR spectra is often affected by the coil angle, and often it seems that it's better to do these experiments in a coil parallel to the magnetic field instead of perpendicular. So for example, I'll just compare this to one of the original Overtone NMR spectroscopy papers, where you see their simulations here, for example, where they have when you include all intensities when the coil is perpendicular to the magnetic field and when it is parallel to the magnetic field. So this is for an asymmetry parameter of 0, so this line shape corresponds fairly well to this one here. And if we change the coil angle to 90 degrees, we in fact get this line shape here. We can change the asymmetry parameter to 0.2, and there's very little change in the line shape for the spectrum in a coil perpendicular to the magnetic field. But if we change the coil angle to 0 degrees, you'll see this extra singularity, which corresponds to this spectrum here, which can be useful for simulating or for getting your quadrupolar and chemical shift tensor parameters for these overtone transitions. So I'm going to open an experimental nitrogen-14 overtone spectrum that I have acquired. So this is for glycine. So this is the experimental spectrum here, and I'm just going to read in the NMR parameters for this site, which I obtained from the literature. And so this is the simulation of this NMR spectrum. And so you can see that if for example, I had acquired this spectrum in a coil, I have acquired it in a coil perpendicular to the magnetic field, so this is the line shape that I have. Although if I acquired it in a magic angle spinning probe, for example, the line shape would have looked, well, actually quite similar. But the line shape changes somewhat as you change the coil angle. And again, you can notice the chemical shift axis here. I referenced it to the nitrogen-14 single quantum transitions. And so the chemical shifts for the overtones actually appear at around 1 million ppm. So you can change the axis to frequency, for example, so you can actually see that this is at double the Longmore frequency that I have entered. So I hope you enjoyed this video, and thank you for watching this series of Quest tutorial videos.